All right, so 521 is verifying trig identities. These notes are like mind-blowing. They're just great. It's all in one line. I have all the notes in one line, and then we're just going to do examples. I know, it's crazy. Pick the ugly side. And make it better.
Oh my God.
That's it. That's the notes. Now, by ugly side, I do mean more complicated. Just to be clear. And since we're only making one side better, that's kind of saying that we are not touching the other side. One side you cannot change at all. You can change nothing about it. We're not like solving equations. We're only working on one side. We're proving that one side is the same as the other side. So we can only change one side. And taking the easier, nicer side and making it more complicated sounds way harder. I've actually never tried to do it that way. So first example, so you know that what I'm talking about, would be cosecant theta sine theta equals 1. Cosecant theta sine theta equals 1. So in this case, the more complicated or the ugly side is going to be the left-hand side. Obviously, because 1 is pretty simple. There's not much we could do there. I like to show which side I'm working on by doing something like that, being like, that's the side I'm going to work on. So I'm not going to do anything to the 1. It has to equal 1 every single step. All right, so if I have cosecant and sine, and I know I want it to equal 1, there's not a lot I can do here, so I'm just going to turn my cosecant, turn everything into sines and cosines. And any time one thing is a fraction, make everything a fraction. So either everything is a fraction or nothing is a fraction. So if I'm turning cosecant into 1 over sine, then I need to turn sine into a fraction by calling it sine over 1. And it equals whatever's on the right-hand side, which I'm not, on this problem it's not, okay, on this problem it's not a big deal because it's just 1. But normally I'm not going to write what it's equal to. I'm just going to write equals and then not even write what's on the right-hand side. So I'm not tempted to change it because you cannot change it. And so now I see I have 1 over sine times sine over 1. So if I multiply these, I have a sine theta in the denominator and a sine theta in the numerator. So I'm going to cancel those out. And now I have 1 over 1, which is 1. And that equals 1. So it has been verified. I verified it. So last period, someone asked me, so what part is my answer? Well, the whole thing is the answer. It's like the process of showing each step, like as if someone else is looking at it and you're trying to show them the process of making them equal. All right? So example 2. Secant theta, parentheses, 1 minus sine squared theta equals cosine theta. Again, it's pretty easy to see which side is the ugly or complicated side. It's going to be the left side. So I'm only going to work on the left side, and I'm not going to do anything with cosine theta on the right. All right, so if I know I want all of this to equal cosine, I figure out what I'm going to do. Well, I know I can see, I also have my formula sheet in front of me. This is a 1 plus or minus function squared. Looks a lot like Pythagorean. So I'm going to take that over to the side, and I'm going to take the Pythagorean identity, which is sine squared theta plus cosine squared theta equals 1, and see if I can make it match what I have in my problem. In my problem, I have 1 and sine squared together. So if I want to move sine squared over there with the 1, I have to subtract. So that would leave cosine squared theta equals 1 minus sine squared theta. And that works because now the right-hand side of my identity matches what I have in the problem. So I'm able to remove it from the problem. And in its place, I can put the other side of the identity in its place. Cosine squared theta is going in place in the parentheses. Cosine squared theta. And I have the rest of it. Secant theta. And equals whatever's on the right. All right, so I see that I am trying to get the left side to be just cosine theta. And I look at it, I have cosine squared, so that's pretty good because I want a cosine. But I have a secant. There's no secant on the right, so I can turn secant into 1 over cosine. And remember what I said a minute ago, if you turn one thing into a fraction, turn everything into a fraction. So I'm going to make cosine squared theta a fraction by putting it over 1. And that equals whatever's on the right. All right, so then I look at this and I'm like, okay. I have cosine. I'm going to multiply these two fractions. There's a cosine in the denominator, and there's cosine squared in the numerator. I can cancel the squared with a cosine. So now all that's left on the left is cosine theta, and that equals whatever's on the right, which is cosine. Whoa, I put theta right there. I didn't mean to do that. Just a cosine. Cosine theta equals cosine theta. It is verified. And if you want to show that there's something every time, you can just do that. But I think doing it that way, where you don't write what's on the right-hand side every single time, is going to keep you from making a mistake by changing it. Okay. Example 3. This time I have sine of negative theta over cosine of negative theta equals negative tangent theta. All right, so I want to make the left side match the right side. So I see that I have sine over cosine. And as long as whatever is in the parentheses is the exact same thing, it doesn't matter what it is. So yes, it's negative theta instead of theta, but it's sine of something over cosine of the exact same thing. So that means I can turn sine over cosine into tangent. So tangent of negative theta. And it equals whatever's on the right-hand side. All right, so I have tangent negative theta. I'm like, okay, well, what am I going to do with that? So I look at my formula sheet because I'm kind of stuck. I'm like, I don't really know. And when I do that, I see there is the even-odd identity. And the one that has tangent in it tells me that tangent of negative theta is equal to negative tangent theta. And so I look at my problem and match this with the left side of the identity. Tells me I can remove it from my problem and plug in the other side of the identity. So negative tangent theta is equal to whatever's on the right. And what is on the right? Negative tangent theta. So it has been verified. Good? Any questions? Everybody okay? All right. Then we'll keep going. Example 4. This one we have sine squared theta sine squared theta parentheses cosecant squared theta minus 1 equals cosine squared theta. All right, so again, the left side is the complicated side. So that is what I want to simplify to be cosine squared. So I look at it, I'm like, okay, well, where do I want to start with this? It seems like a lot going on over there. But I have a function squared, a plus or a minus and a 1. Again, it looks like that Pythagorean identity. So if you're going to use that, you need to write it over here on the side. This is the one with cosecant in it. We haven't really done much with that. So that form of the Pythagorean identity is 1 plus cotangent squared theta equals cosecant squared theta. What I have in my problem is cosecant squared theta minus 1. So that means I want this 1 to go over there with cosecant squared. So I need to subtract it. So cotangent squared theta equals cosecant squared theta minus 1. And that is exactly what I have in my problem that I'm trying to verify. So that's the part I'm going to remove. And the other side is what I'm going to put back in its place. All right, so now I have sine squared theta, and in parentheses, I'm going to put cotangent squared theta. And it should equal whatever's on the right, which is cosine squared theta. So I didn't really still don't have any cosines in there, but I did simplify it a little bit because I started with a binomial in the parentheses, 2 terms, and now I just have a single term in parentheses. So that's helpful because I only have a single term on the right. So I have simplified it. And now I have sine squared and cotangent squared, and I'm looking for a cosine squared. So I don't have a cosine, but I know there's cosine is inside of that cotangent. I just need to get it out. So I'm turning everything into fractions. Sine squared theta over 1 and then cotangent squared as a fraction is going to be cosine over sine. So, and since it's cotangent squared, it's going to be cosine squared theta over sine squared theta. And it equals whatever's on the right. Okay. So now I'm going to multiply these fractions together. I see I have sine squared in the numerator and sine squared in the denominator, so they will simplify to equal just 1, or as we say, cancel out. And all that's left is cosine squared theta. And it equals whatever's on the right, which is also cosine squared theta. This is all the same on the right-hand side. We didn't change it. It verified. They are exactly the same. All right, I'm going to go over 2 more. All right, so my example 5 is the most complicated of the ones that I'm doing today. But it's okay. You can still do it. It's not that bad. Example 5. I just want to get you ready for that. This is the most complicated of today's examples. Secant to the 4th x minus tangent to the 4th x equals 2 tangent squared x plus 1. So what I've been saying is take the ugly side or the more complicated side and make it better. Well, these both look complicated and ugly, right? So you want to get the more complicated. So the one with the higher degree is going to be more complicated. Here we have 4th powers. There we have 2nd power. Because they're both binomials. There's 2 terms. Here's 2 terms. So that doesn't really help. But these are 4th powers. That's a 2nd power. That's power 2. So we are going to simplify. We're going to work with the side on the left. And we will not change what's on the right through the whole problem. We have to make the side on the left match the right. So where I'm going to start with this is, I know we talked about doing difference of squares and reverse difference of squares the other day. But I'm going to write a little formula just to be clear, because this is with secants and tangents to the 4th, and I know that can be scary. Difference of squares. If I write this as a formula, it makes it a lot simpler to look at. So if I wrote this as a to the 4th minus b to the 4th power, and I tell you to factor it, because I want to factor this. Difference of squares is when you have subtraction and both terms are perfect squares. You can tell if it's a perfect square because of the exponents. If it's even exponent, then it's a perfect square. So I can factor this by making 2 sets of parentheses. One's positive and one is negative. The square root of the first term will give you the first term of each. So square root of a to the 4th is a squared. The square root of the second term will give you the second term of each. So b squared. All right, so that's difference of squares. I know you guys know difference of squares. You've been doing it a long time. So now we're going to do that with secant to the 4th x minus tangent to the 4th x. That's difference of squares. So we can factor this relatively easy by following this format. I'm going to make my parentheses big because we are putting a lot of stuff in them. Since it's subtraction, perfect square, I do one's positive, one's negative. Square root of secant to the 4th, that's like my a value, is going to be, I did a squared, so secant squared, secant squared. Secant squared x, secant squared x. My second term of each factor is the square root of the second term. So it's the b. So that's going to be tangent squared, tangent squared. And it's equal to whatever's on the right. I'm not even going to write what's on the right, just equals. Okay, so now that I did that, I don't have 4th powers anymore. I am down to power 2, but it's still pretty complicated looking. But it does seem like it kind of looks like Pythagorean. I don't know which one is going to be my Pythagorean, but it's trig function squared plus or minus a trig function squared. So I'm going to look at my formula sheet and find the Pythagorean identity that matches secants and tangents. And it is tangent squared theta plus 1 equals secant squared theta. And I should be able to rearrange this to match one of these sets of parentheses. I just don't know which one. Is it the positive or the negative? So secant and tangent need to be together. In the identity, they are not. So if I subtract tangent from both sides, then I get 1 equals secant squared theta minus tangent squared theta. So I look at my problem. Where do I have secant minus tangent? Secant minus tangent is this one. That matches. So that tells me I can remove it from my problem. And in its place, I could put what's on the other side of the identity. That's what's going to go in there. 1. That's super nice that it's a 1 because I'm multiplying by that set of parentheses, and I just turned it from that mess into 1. And I know this part, most of you probably would not want to write this down or the next step, but when you're doing verifying identities, you need to show all the little teeny tiny steps. So now I didn't do anything here. Secant squared x plus tangent squared x. But the second set of parentheses, now I'm putting 1 in there. So I'm showing that I turned this into 1 by the Pythagorean identity. And it equals whatever's over there. So then if I multiply the two sets of parentheses together, now I just have secant squared x plus tangent squared x equals whatever's on the right. Because if you multiply by 1, it's just whatever it is. Okay, so I'm getting closer. Let me do it once you get through a little process. Do a quick check. Where am I at and what am I trying to get to? I'm trying to get to 2 tangent squared x plus 1. I have secant squared x plus tangent squared x. So I do have a tangent squared x, and I want 1, so that's good. So I want that to stay in my problem. But the right side doesn't have a secant squared. So that's a problem. And you figure out how can I get secant squared out? Well, I just saw secant squared a minute ago, didn't I? It was right here. There's a secant squared right there, and it equals something. So I could use the identity. Normally we use the identities, or we have used the identities to make things simpler, to make it more simplified. This time we're not making it more simplified, but we're making it closer to what we're trying to get to in the end. We have a secant squared x that we want out. The Pythagorean identity has a secant squared x. So we could take it out of our problem and put the other side of the identity in its place. Even though it's technically more complicated, it's more suitable for our needs. So I'm going to put in tangent squared x plus 1. And I still have tangent squared x. So plus tangent squared x. And it equals whatever's on the right. All right. So now, tangent squared x plus 1 plus tangent squared x. These are like terms. They're the same thing. I have one term here and one term here. 1 plus another 1 is 2. So now I have 2 tangent squared x. And there is a plus 1. That is not a like term, so it has to stay by itself. Equals whatever's on the right. So what's on the right again? That is the same thing. So I'm going to write it 2 tangent squared x plus 1. This stayed the same all the way down, and I verified it. Left side matches the right side. So again, I know that one's kind of complicated. It's different. Use some different thought processes there. Trying to get it to match, not necessarily always simplify, but match what's on the right. I'll do one more problem today. This one has a lot of lines of writing, but I don't think this one's necessarily extra difficult. It's just simple, a lot of simple steps. So example 6. We have secant x minus tangent x times sine x plus 1. And it equals cosine x. All right, so now we want to verify that all of that on this is the same thing as simply cosine x. So we see we have a binomial times a binomial. One is negative, one's positive. And all this talk of difference of squares might make you think maybe I could do that. But this is secant, that's sine. This is tangent, that's 1. Not the same thing. So we cannot do that. This is a binomial times another binomial. So we have to multiply this out. When I multiply out, I do FOIL, which is first, outside, inside, last. I know a lot of you do box method. That's fine. You can multiply this out however you want to multiply it out. FOIL method is first, outside, inside, last. It tells you which terms you're multiplying together. So I'm multiplying the first terms together. Is secant times sine. The nice thing about multiplying these trig functions is you're not calculating because there's no numbers there. Secant times sine is secant sine. So secant x, sine x. And then the outside terms is the 2 on the outside. So secant x times positive 1. Well, it's positive, so I'm going to put a plus sign. And then I have secant x times 1, so it's secant x. Then I'm going to multiply the inside terms. I have a negative times a positive, so it's going to be negative. Tangent times sine is tangent sine. And then my last terms, negative tangent times positive 1. Negative times positive is negative. Tangent times 1 is tangent. Equals whatever's on the right. Not even writing it. So I multiplied it out. And then I looked to see, can I combine any like terms? Do I have any like terms? Secant sine, secant, tan sine, tan. No, I don't. Yes, there is a secant here and there's a secant here, but this one isn't just secant, it's secant sine. That one's not secant sine, so I cannot put them together. And I know I look back at what I'm trying to do. I'm trying to get them to a cosine. There's not a single cosine in here anywhere. So the next thing I'm going to do is make everything sines and cosines. See what happens if I do that. Get rid of any secants, tangents. Get rid of all the secants and tangents. Make them sines and cosines. So that means I'm turning everything into a fraction. And I'm going to put parentheses since I have things together. So secant x is 1 over cosine x. Put in parentheses. Sine x, if I'm going to make it a fraction, I'm going to put it over 1. So sine x over 1. Plus sign is a plus sign. Secant x is 1 over cosine. A minus sign is a minus sign. Tangent x is sine over cosine. So sine x over cosine x. There's a sine x. I'm going to write it as a fraction. So sine over 1. Minus sign is a minus sign. Tangent is sine over cosine. So now everything is sines and cosines. And then I'm going to look at it again. See, now is there anything I can do? Well, yeah, I have these two pieces that are fractions being multiplied. So I'm going to put those into a single fraction for my next trick. So here this is going to be 1 times sine is sine, cosine times 1 is cosine, so this is sine over cosine. Bring down the plus sign. I didn't do anything here, so 1 over cosine. Minus. I have two fractions multiplied together, so on top it's sine times sine, so that's sine squared. On the bottom I have cosine times 1. So that's cosine. Minus, stays a minus sign. And then I'm not doing anything with that one because it's a single fraction. And it equals whatever's on the right. Okay, that looks better. And now that I'm looking at it, I see they all have a common denominator. The denominator in every single one of these is cosine, 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 cosine. So that means I can write out the numerators and put them over a single cosine. So I have sine x plus 1 minus sine squared x minus sine x. And all of that is over cosine x because that is the common denominator. Okay, so I put all the numerators over one single denominator. Now I can look to see, can I combine any of those in the top? Are there any like terms in the numerator? Yeah, there are. I have sine x plus 1 minus sine squared minus sine. I have sine minus sine. So those just kind of go away, right? Sine minus sine goes away. Sine x, negative sine x, cancel each other out. So now I have 1 minus sine squared x left on the top. And all I have on the bottom is cosine x. That equals something on the right. What is it supposed to equal again? Oh yeah, cosine. All right, we're not quite there yet. We have a 1 plus or minus a sine squared x. That looks a lot like Pythagorean, doesn't it? Because it's a 1 plus or minus a function squared. I'm not writing this one out because we've been writing it out a lot. And it's just the sine cosine one. But I am making a note that it's the Pythagorean identity. So if we're using the Pythagorean identity, we can bring out this and we can put in cosine squared. Oop, I almost wrote theta. It's an x. Cosine squared x. And the denominator is a cosine x. Equals whatever's on the right. If I have cosine squared x over cosine, cosine x and the squared cancel each other out. So now I have cosine x equals whatever's on the right, and what was on the right? Cosine x. So this cosine x stayed the same all the way down. And we verified it. It is the same. Cosine x equals cosine x.